One of the things that we want to touch on before we move on to the next section is in the solution, when we're finding these functions u1 and u2 as a part of our variation of parameters method, why do we not concern ourselves with the constants of integration? I mean, that's something that, back when you're taking Calc 1 and Calc 2, it's kind of drilled into your head that whenever you do an antiderivative, you should have constants of integration. And the answer is they're not necessary because let's suppose that we were to include them. So let's suppose we look at our solution here. So we have y would be equal to yc plus yp. That's the solution to our second order right now linear differential equation. And let's suppose we know that yc has the form c1 y1 plus c2 y2. So this is yc. To this we would add our particular solution, which we know has the following form. So we know it's going to be u1, and let's suppose we did include the constant of integration. Let's see what would happen. So if I add, that's constant of integration, let me just call it k1. And we know that gets multiplied to y1. And now let's suppose we have u2, and suppose I include the constant of integration here, I'll call it k2 times y2. Well, if you distribute that constant out, because ultimately this expression gets multiplied to y1, what we would get would be u1 y1 plus k1 y1. And similarly, if you distribute this out, you would get u2 y2 plus k2 y2. However, this constant times y1, that was already considered and included in our complementary solution. I'm not sure why I'm calling this y2, that's yc. And then similarly, whenever we look at the k2 y2, which would be this term here, that's already included here. We already have a constant times y2 as a part of our complementary solution. So essentially those are kind of redundant. We don't need them, so we can leave those off. So we don't include the constants when we do the integration to find u1 and u2, because those would ultimately just factor back into our homogeneous solution yc anyway, so that complementary solution. So the thing that's nice is we actually have a way to solve this. However, one of the things that we know, the key step in being able to solve for u1 and u2 is ultimately the ability to do these kinds of integrations. So if you remember, u1 prime was defined as this expression here. It was the negative of y2 f of x divided by w of x. And u2 prime was y1 f of x divided by w of x, where we anticipate being able to do these integrations. However, given just some random functions, f, it might not be possible to explicitly solve and actually find the exact value as a closed form function for u1 and u2. So oftentimes, depending upon the problem, the best we might be able to do is to represent the solution in integral form. This is something we've encountered earlier in the class, where we can sometimes write u1 as being that integral from x naught to x, and u2 similarly is the integral from x naught to x, using the dummy variable t for our functions in integration. After all, once you do integrate this and you evaluate it at x, this will become a function of x like we see on the left-hand side for both of them. We only require that the integrand be continuous on the closed interval that contains x0 to x. So let's take a look at one example of this type. And then this will finish off section. Not sure what's happening here. Hold on one second. So let's do one more, and then this will finish off 4-6. We want to solve y double prime minus y equals to 1 over x. And on the surface level, this looks kind of innocent enough. It's pretty big. It's pretty nice. Doesn't look any difficult than perhaps the first two examples we've already done. So let's see what's going to happen here. Step 1 is still going to be the same. I'm not sure. I apologize. I'm not sure what's going on with this thing. Okay, I think I got the whiteboard figured out. Let's give this another try here. So we want to solve y double prime minus y equals to 1 over x. And maybe I did not. My apologies. Well, let's see how much we can squeeze in here. So step 1 is the same. We want to solve for yc first. That means we need to solve the homogeneous differential equation. Our auxiliary equation would be m squared minus 1 equals to 0. Factor it, this is the difference of squares, or you can use the square root property. Either way, we're going to get m equals plus or minus 1. So our complementary solution is going to be y equals c1. We're going to have an e to the negative x. And then we're going to have a c2 e to the positive x. So that part's done. Now we want to find our particular solution, solve y sub p, and we're going to use variation of parameters to do this. We assume that y sub p is going to be equal to u1 times y1 plus u2 times y2, where y1 is this function here, and y2 is that function there. So y1 is e to the negative x, y2 is going to be e to the x. And we know we need the Wronskian in a minute, so I might as well just go ahead and also compute these derivatives. So to find u1, remember u1 prime is going to be equal to the following. u1 prime is equal to the negative of y2 times f of x divided by w. For this differential equation, f of x is 1 over x. So that means that u1 prime is going to be equal to the negative of e to the x times 1 over x. And we need to compute w. Let's go over here and do that. Our Wronskian is going to be the determinant of y1 prime would be the first column. And then y2 prime would be the second column. Multiply the diagonals and subtract the major diagonal and the minor diagonal. We're going to get e to the negative x times e to the x minus a minus, ultimately, like this. So we get the following. We get, this will be 1, minus a minus will become a plus 1, because e to the negative x times e to the x is e to the 0, which is 1, and so we get our Wronskian to be 2. So let's go ahead now and work this out. So it's e to the negative x times 1 over x divided by 2, which we can write as negative e to the x divided by 2x. Now, to find u, so u1 prime, dx would be equal to the integral of this thing with respect to x. However, this integral here is not an elementary antiderivative. So that's not one we're going to be able to get a closed form for. So we could numerically now analyze it if we wanted to. So what we're going to do instead is we're going to write it like this. So I'm going to call u1. I'm going to switch to the variable t for integration. And because I'm doing that, let me show the dependence on x here. We can integrate from some x0 to x of negative e to the t divided by 2t dt, and that would be an integral representation for our u1. Similarly, if we want to solve for u2, u2 prime is equal to y1 times f of x divided by the Wronskian, which is going to be 2. Our y1, if you recall, was e to the negative x. So now this is going to be e to the negative x times 1 over x divided by 2, which is going to be e to the negative x divided by 2x. Again, to solve for u2, we would want to integrate both sides with respect to x. And unfortunately, this integral is, again, it's not an elementary antiderivative. So we're going to represent u2 as an integral as well. So let the integrand be defined as x naught to x. Then u2 of x is going to be equal to e to the negative t divided by 2t dt, that antiderivative. And we can write out our final solution now. Again, it's going to be, portion of it will be represented in integral notation. But here's what we get. So our general solution is going to be the complementary solution, which we had down here, that's c1 e to the negative x plus c2 e to the x, plus now it's going to be y1 times u1, which is this thing right here. So that's going to be plus a negative, and actually let me pull this negative out of here, just to save from writing so many signs. So it ends up being a negative y1, which is e to the negative x. I pulled this sign out, but I'm going to have the integral from x sub 0 to x. Sorry, I pulled it out. It's going to be e to the t over 2t dt, and then plus u2 times y2. Well, y2, I'll put that term first. y2 is e to the x. And then u2 is the integral from x naught to x, e to the negative t over 2t dt. And this would be our general solution. Recall that f of x was equal to 1 over x. The Wronskian was constant. It was a constant function of 2. y1 is e to the negative x. y2 is e to the positive x. All of these functions are defined and nice, except for f when x is equal to 0. So the solution we're giving here, this is kind of important to summarize too, is valid over any closed interval x naught to x that does not contain 0. So as long as 0 is not contained in that interval, because f of x is undefined at 0, then this would give us the integral representation of the solution of that differential equation. Fun stuff.